Okay, welcome to the last lab of EE310. This is a lab on power amplifiers, and what we're going to be doing is testing a Class B amplifier, and then we're going to test a very convenient way to do a Class AB using an op-amp to absorb the deadband instead of those two diodes. And this is a circuit that might help you out. It gives pretty nice results and much easier to implement than the pair of diodes and the biasing network for them. So we're going to first start with a Class B amplifier using our good old 2222 transistor for the upper half, and then a 2N2907 PNP transistor for the lower half. That one has the pinout we're used to, but these come in a metal package. There's a metal tab over here on one end, and it goes EBC from there. They have a lower beta than they're used to, but they still work fine. So we have also these 47 ohm resistors here. Those are just short circuit protection in case anything goes wrong. It won't immediately vaporize your transistors. We're just going to build this amplifier, test its response to different amplitudes of VS, test its response to different frequencies of VS, and then we're also going to do load testing on it. We're going to, most of it with a 1K resistor, then we're going to switch to a 100 ohm resistor. Then we'll actually try it with a live speaker, and we'll actually be able to see what these waveforms look like. We'll also see that as the loading gets a little bit heavier, the waveforms tend to distort a little bit more. And then once that we're done with that, we're going to modify our circuit, placing this 741 op-amp in place here. And the way this works is the following. The op-amp has the principle called virtual null. Virtual null means that the voltage here and the voltage here have to be the same for the op-amp to work. So what we're going to do is we're going to set the op-amp so that the VS, the input voltage, is exactly matched by the output voltage over here, and the op-amp will swallow up the deadband. So if you were to do a response to the op-amp, it would look like this, to a triangle wave. It'll immediately jump from minus 0.7 to plus 0.7, and it'll jump right over the deadband, and the output here will be a very good match for the input over there. And so this is using the op-amp, the virtual null principle, where it keeps these two inputs the same to get V out to exactly match V in. And we'll see that the response actually does this. So both circuits are really easy to build. Double-ended power supply. We are going to need a double-ended power supply. And we'll also test this with different waveforms and see what they look like. So that's just it. Not a whole lot of calculations to do. We're just going to build it and watch and listen to it. So here we have our setup. We have our Keysight 33500 Series B signal generator number 793. We have our Agilent dual DC power supply E3620A number 688. And we have our Tektronix MSO 2012 mixed signal oscilloscope number 635. And our standard breadboard. So I have wired the power supply here so that we have the left side supply negative tied to ground, the right side supply positive tied to ground. So this will be our plus 10, 12, this will be our minus 12, and any of these three in the middle will be our ground. So we have the ground lead already connected to the board. We have this wire here is the plus 12 that connects over here on the left, and this other red wire here is the minus 12 that connects here all the way to the right. So this will be our minus 12, plus 12, and then ground in the middle. And then we can start building. So here is our 2222 transistor. It goes EBC. So I'm just going to place it right there on the board, like so. And then here is our 2N2907. And you can see the tab over here is on the left side. That's where the emitter is. And the way this circuit is built is the emitters are tied together. So I'm just going to plug the emitters into the same row. So EBC, like that. So now both emitters are in the same row. And the emitters are going to be our output. So let's take our channel 2 probe and connect it to the emitters up here. And also we're going to have our load resistor. So let's start with a 1K resistor to be our load. We're going to do the first experiment with a 1K load resistor and just see what it looks like. And we're running that to the ground lead, which is the upper bus on the bottom. And now we just need our 247s. So the collector of the PNP goes to -12, collector down to this very bottommost bus, which is -12. And our other 47 is the collector here goes to the +12, which is the upper bus there. And then finally, we just have to connect our two bases together and connect those to the input. So I've got a short jumper here, connecting base to base. Okay, moving that over to there. And we want to go base there to base there. If I was really clever, I would have assembled the circuit. But I like to kind of separate the output from the input. And then we finally have our input here on this green wire connected to channel 1 of the oscilloscope, can go to either one of these bases. And it looks like there is a spot free over here. So that completes the wiring of our circuit. Double checking, collector, emitter to emitter to the 1K to ground, collector up there, and we can go ahead and turn it on. And looking at the waveform, we can see we've already got some of this waveform here. Let's see what this looks like. The power supply is turned on. We have a signal there. So as we crank up the ground, oh yeah, one of these has to be grounded, yes. Let's ground the scope, like so. And it looks like we can already see kind of a response there. So as we make our amplitude smaller, let's say we're going to make our amplitude 1 volt peak to peak. And what we see, I'm going to set these both on the same scale, is that the signal just barely makes it through. This is a 1 volt 1 volt signal, 1 volt per division. So we can see this is plus or minus 1 volt. And we can see that it's just showing up a little bit. We're losing about 0.7 of a volt there. If we make this any smaller, now it's 1 volt peak to peak and the output wave is completely gone. So this is the deadband swallowing up a small signal. So we'll make it bigger again, and then let's make bigger steps making it bigger. And what we'll notice is that as the waveform gets larger and larger in amplitude, the step becomes less and less conspicuous. So now we're up to 4 volts peak, and the step is smaller, bigger still. Oh, thank you. Bigger still, and you notice the wave gets bigger, and the step becomes smaller and smaller in proportion. So there's a nice big sine wave that's 10 volts peak, and the step is really a lot less noticeable. If we switch to a square wave, what we'll notice is that there is no sign of the step. It's been swallowed up. So the square wave doesn't show that at all. And if we switch to a triangle wave, we can see that also with a big wave, the step is reduced. But as we make our amplitude smaller, again, it becomes more and more pronounced. So here again, we have a 2 volt peak wave, and only about 1.3 volts is coming through. The deadband here is swallowing the rest. So let's put this back on sine wave, and let's check the frequency response of this thing. So we mentioned in class of gain bandwidth product that the more gain you have, the less bandwidth you've got. And this circuit only has a gain of 1. So we should expect to see a pretty good bandwidth. Let's see what it looks like. So right now we're running at 440 hertz. Okay, and so let's just start to sweep the frequency upward and make a note of our amplitude. So we're at peak to peak, 2.76 volts. And we're just going to continue to sweep it up, and we'll see that it's really staying pretty steady. We are now at 2.6 kilohertz. That's 3 kilohertz. Still 2.76 output. So now let's go to 4 kilohertz, 5 kilohertz, 6, 7, 8, 9, 10 kilohertz. We're still rock steady there. That's pretty good. So let's continue to raise this and just see how far we can go. There's 20 kilohertz. We're still at 2.76. Let's try 30 kilohertz, 40 kilohertz, 50 kilohertz, 60. We're getting pretty good bandwidth out of this. In the audio world, we have arrived that once you get to 20 kilohertz, that's basically the full range of audio. Now you notice there's a little bit of offset in the two dead bands here, and that's just because of the timing, but we still have the full output. So there's 300 kilohertz, 400, 500, 600, 700, and we're still at 2.8. We're still at full amplitude. But we'll notice now the waveform starts to get distorted. So let's just still keep going. There's a megahertz, and we're still getting the full waveform coming out. That's not bad at all. How about 2 megahertz? It's still, there's distortion to the wave, but it's still full amplitude. 3, 4, 5. 5 megahertz, but it's still making the full wave. 6 megahertz. 10 megahertz. Now the dead band is gone just because the signal is too fast for it, but we're still at a full strength output. It's also strange that the input signal is getting bigger at these frequencies. That's unexpected. But the output is still there. We're at now 20 megahertz, which I think is as fast as this can go. And at 20 megahertz, we're still making the full wave output. So it's got remarkable bandwidth. So we've seen that we have very good frequency response out of this circuit. So now we're back to 100 kilohertz. Let's bring it down to, I don't know, 10 kilohertz? Let's go to 5. Okay, so at 5 kilohertz, we've got nice clean waveform again. Now let's check the loading. So what I'd like to do is I'm going to replace the 1K resistor with a 100 ohm resistor. And then we'll see how that does. So I'm going to pull out the 1K resistor and put in a 100 ohm resistor. And we'll see if we still get good waveforms. And it looks like we do. We now have a 100 ohm resistor in there, and the waveform still looks good. And so what that tells us is this amplifier has a nice low output impedance. It's able to drive a heavier load. That's a 100 ohm load. Let's push our luck and try to go to a 10 ohm resistor. Now we're really making this thing work. So we're going to pull out the 100 ohm resistor and put in a 10 ohm resistor and see if it still holds up. Not bad. Even driving a 10 ohm load, brown, black, black, the waveform still looks good. Now you notice when I touch it, it came up with some oscillations, but I think that's just me, my electric personality. So a 10 ohm load, it still works. This resistor at this level actually could get hot. Let's just crank up the amplitude and see if it keeps on working, because that means we're drawing more and more current. Now we're starting to get a little bit of clipping at the top and the bottom, and that is about a 3.3 volt wave. So what's happening, we're running out of base current to drive the transistors, but we're still able to make a 4 volt peak to peak wave across a 10 ohm load. Not bad, and these are not even power transistors. And now for the ultimate, let's try it with a speaker. So we have a loudspeaker here. We're going to replace it in place of the 10 ohm resistor. Now the trick with the loudspeaker is that it's also an inductive load. I'm going to turn it down because the noise is annoying. So you not only have to worry about driving the current, but you've also got to worry about driving an inductive load, which do not like changes in current. Yes, this is the lab where everybody gets a headache. So right now we're listening to 5 kilohertz, and you can see that there is some distortion to the wave because we are now driving an inductive load. It drives about the same amount of current, but the inductive load gives us these spikes when it turns on and off. And the message for that is driving a speaker or an inductive load like a motor is always going to be more complicated than driving a resistive load. So let's see how this does. This is where we get to play with the different waveforms. So let's see how high we can hear it. That's 5 kilohertz, 5.1, There's 7 kilohertz. We can still hear it. I can still hear it. I don't know if the audio system on the recording is going to be able to pick it up. 8 kilohertz still coming through just fine. 9 kilohertz. 10 kilohertz, I can still hear it, which is not bad for somebody my age and all the loud music I listen to. 11 kilohertz, now I'm starting to lose it, but I'm not sure if it's my hearing that's losing it or the speaker itself just can't go to that higher frequency. Most speakers have a frequency limit. There's 12 kilohertz, I can barely hear it. 13 kilohertz. So, and again, now I'm starting to really lose it. And by the time it gets to 14 kilohertz, I cannot hear it anymore. Can you hear it?
Barely.
Barely, okay. And let's see how low this goes. And now we're getting into the prime of human hearing. Human hearing is best between 500 and 2000. And this is where it's going to sound the loudest to us. There's 1000 hertz, 1 kilohertz. The waveform looks pretty good. 900, 800. And there's 100 hertz. By the time we get to 100 hertz, it doesn't come through very well. And there might be the speaker doesn't do very well at 100 hertz either. But it is playing. So let's make it a little louder. And you can see the amplifier is unhappy making bass, making low frequencies. So that is the Class B amplifier. What we're going to do now is modify the amplifier to make it into Class AB using an op amp. So we're going to rewire it. I'm just going to temporarily shut off the power supply. We can leave everything else going. You also notice there's a little bit of bleed through because the transistor from base to emitter is still a diode. And so what we're having now is the signal generator driving the load. And you can see the signal generator is straining and the load is really nothing to be too proud of either. So we're now going to install our 741 chip a little bit off to the side. Okay. And some jumpers. We need to connect pin 4 to -12. I'm going to put the jumpers at the bottom and well out of the way. And -12 is the bottommost bus. Okay, and then pin 7 goes to +12. Looking for a decent wire. Yeah, that just is bleeding through from the signal generator. Yeah. So a decent jumper from pin 7 to +12. And now we're going to connect our signal generator here over to pin 3. Okay. And then we're going to connect the output from pin 6 over to the input here on the 2 bases. Right there. And then we're going to connect pin 2 over to V out. So we need one more jumper to connect from V out. Do we have a spare lead? Yes, we do. To pin 2. And that should be everything. So we have our signal generator going to pin 3. We have we have pin 4 tied to -12, pin 7 tied to +12, and we have the output 6 going over to the common bases. Okay, and then we have the output here coming back to pin 2, that's the blue jumper. So that should be good. Let's cross our fingers, turn it on, and see what it does. We have a little bit of oscillation in there, and that's probably a disturbance in the power supply. Do we have any capacitors handy? I know there's a few of them around. That fuzz is oscillations in our power supply. And so if we can put some, okay. I think there are some discrete capacitors in And Conwell's got a tray over there that's got some discrete capacitors as well. But let's just see, these all seem to be oscillations in the upper half. So let's see if we can bypass the upper half to make those go away. That's better. Oh, yeah, that should help. And the electrolytic capacitors are not very good at high frequency. This one's not helping much either. Okay. I wonder if I can put another capacitor on the negative side, see if that makes a difference. Oh, there it does, yes. Okay. So the capacitor on the power supply cleans up these oscillations, and what we see now is we have a beautiful output waveform. We have the crossover distortion is gone, and it looks perfect. So let's try a triangle wave. A triangle wave is where this will really show up. And again, in a triangle wave, we have a perfect smooth transition right here. And this is acting like a class AB amplifier now. So we can listen to them, and hopefully they're a little bit more pleasing to listen to than the last one was. It has a lot of clipping in it. So we can turn up our amplitude. A little bit of clipping in there. The clipping is now because the 741 can only put out 25 milliamps of current. It can't drive the load very well. So let's put it back on sine wave. Okay, and see if we can hear it. What frequency at? We're at 100 hertz, so let's bring it up. That's 300 hertz. And it's certainly more pleasing to listen to than the clipped sine wave was. And so it's at 400 hertz, amplitude, and we can see some clipping now. We can see it in the waveform, we can hear it. But even if the waveform gets very small, it doesn't get swallowed up by the deadband. That's only 1 volt peak to peak, and it comes through intact. Not bad. So this class AB now, driving an 8 ohm inductive load, makes a pretty nice looking waveform. Let's see if we can see how high a frequency we can get out of this. There's 400, 500, 1 kilohertz, getting kind of loud. Let's turn it down a little bit. This is the lab where everybody gets headaches, or gives headaches, I should say. The people playing with don't seem to mind, but the next door neighbors do. 2 kilohertz, the waveform still looks beautiful. Very nice. There's 5 kilohertz. Again, the waveform looks good. We're starting to see a little bit of crossover distortion here in that notching there, and that's just also its crossover from the push to the pull. There's 9 kilohertz, still looks good. 10 kilohertz still looks good. That's 11 kilohertz, I'm still hearing it, but the waveform still looks good. 12 kilohertz, it's starting to go away in my ears anyway. But you can see that little hint of crossover distortion here with these higher frequency waves. And that's because the 741 just doesn't have a lot of bandwidth either. 13 kilohertz. I can't hear it anymore, but the wave is still there. So let's go up to 20 kilohertz. And it's still full amplitude. So the demonstration is this, using this op amp instead of the 2 diodes for class AB operation works very nicely. And if I had some music to play, we could actually play music through this thing. And you could play music through the speaker as well. So if you have your iPhone with you, you have an output jack, you could actually play music and it would sound not bad. So this is a good circuit if you want to do audiology tests on somebody, determine their frequency range, or you can determine just noticeable difference, like do you hear the difference between this? So I'm changing in 1 hertz at a time. If you hear a difference between that and that, your hearing is much better than mine. Now you can do increments of 10. Well, I can hear the difference between 1000 and 1010. So this is called the just noticeable difference, something audiologists do to determine your range of hearing. And then you could also, how high a frequency can you hear and how quiet a frequency can you hear. So we turn this down, when do we lose it? So at 200 millivolts, it's still there. I still hear it. So a circuit like this is good for doing all kinds of tests on people's hearing. So this is supposed to be just a fun lab. There's not a whole lot of data. All the information is pretty much subjective. So we did do a frequency response. We saw that it worked very nicely with a 1K as well as a 100 and a 10 ohm load. You could make a note that adding these bypass capacitors got rid of that oscillation. It's because the power supplies were unstable. And you can also make a note of how much difficult it is to drive an inductive load than it is to drive a resistance load. We saw those little spikes in the waveform. And you could also make a note of how this op amp works very nicely to convert a Class B to a Class AB. So, last lab, congratulations, we made it through, didn't burn anything up, no sparks, no fireworks, no wounds, no burns. It's a good sign.